In this video I want to try and give a brief introduction to the concept of relative velocity and how it is that we might use vectors to analyze what's going on in this situation. So I'll give a couple of scenarios that hopefully help to explain the concept and some of the key ideas, and then I'll talk about two main types of situation we might encounter. So first of all, let's think about a scenario where maybe you're sitting on a train. So this here represents the train carriage. You're sitting in there on your seat and traveling forwards in that direction. And maybe let's say you're traveling at 80 kilometers an hour. And then there's someone coming along the aisle of the train carriage and they're walking towards you at 5 kilometers an hour. So they're coming along down the aisle. Now, if you were that person sitting on the train carriage there, and I said to you, what's the velocity of the person walking towards you? You would probably say 5 kilometers an hour towards me, or 5 kilometers an hour in the opposite direction to the train, or 5 kilometers an hour. Maybe if we were talking about I's and J's and we were saying, that's the positive I direction, then we would say, well, the velocity of the person walking towards me is just negative 5I. But what about if you were a person standing outside watching this train go past, and I asked you, what's the velocity of this person who's walking down the train carriage? Well, the way you would see that person, they are certainly not going in this direction. They are still traveling very much in this direction, and their resultant velocity would be 75 kilometers an hour in that direction, because the velocity of the train is 80 and they're only going at 5 kilometers an hour in the opposite direction. So that's one example to try and explain the idea of a frame of reference. If you're a person sitting on the train, then your frame of reference is the train itself. And so it's almost like the velocity of this person is considered as if the train weren't moving, because you and that person are both within the carriage. Whereas to this person who's outside the train, we might say their frame of reference is the Earth, and so we might describe the velocity of the person as they see it as the actual or the real velocity. Typically, as people on Earth, we use the frame of reference of Earth as our frame of reference, and so we call the velocities actual velocities or real velocities. So for example, the train traveling at 80 kilometers an hour, that is an actual velocity. Whereas the person traveling at 5 kilometers an hour, we could say that's not an actual velocity, because they're actually moving at 75 kilometers an hour in the opposite direction to the way they're walking. Alright, there's lots of other examples that we could give. I suppose it's important to say, though, your frame of reference could be outside the Earth, couldn't it? You could be, you couldn't really be on the sun, but let's say you could be at the sun and you could be watching the person, both the people on the train. Well, their velocities would be very different from your perspective, because they'd be hurtling along at, thousands of kilometers an hour in the orbit of the Earth. Which would make for quite a different frame of reference. Alright, so there's two main situations or scenarios that we might consider for relative velocity, and the first one is really just the sort of one I described there, where you've got maybe an observer who is external to some system that's going on, and so you're trying to get the true or real velocity from the external frame of reference, which is generally just Earth, or the true velocity. So in that case, it's really a case of resultant velocity, and we're just saying it's the sum of the individual velocity vectors. So here we could say that we can use the sum of individual velocity vectors in order to establish the, let's say, establish the resultant velocity of an object. Alright, and we'll use the language of relative velocity. So let's take another sort of example. This might be one that you've actually experienced, and that is where a person's swimming. So let's say a person swimming at 3 kilometers an hour in a river flowing at 4 kilometers an hour perpendicular to the swimmer. So here we've got the situation where there's a person, this might be you're sort of swimming, let's say at 3 kilometers an hour in that direction there, but the current is flowing, so let's say these are the banks of the river. The current is flowing across you perpendicular to the direction you're swimming in, and it's flowing at 4 kilometers an hour. And so if we use a vector sum there, we could actually add these together head to tail, and we could say that vector there is 4 kilometers an hour. And so the actual or true velocity to a person outside that frame of reference would be that velocity there. And by Pythagoras theorem, we know that's going to have a magnitude of 5. But more importantly, if we're using the language of relative velocity here, we can say, well, that there is the actual velocity of the, let's say, velocity of s for the swimmer. That's their actual velocity relative to Earth, or relative to someone standing on the bank of the river here observing. They're seeing the swimmer go at 5 kilometers an hour in that direction there. The velocity of the water, well, that's this one up here, so let's call that the velocity of the water. And again, that's the actual velocity of the water. That's what the person who's standing on the riverbank would observe. And the other velocity, if we're using the language of relative velocity, this is the velocity of the swimmer relative to the water. So I'll use S rel W as the explanation there. The velocity of the swimmer relative to the water. So velocity of the swimmer relative to the water. So that's velocity of S rel W. And that one's the one that maybe we sort of need to just think a little bit about in order to understand. So that's basically, if you're the swimmer, that's what it sort of feels like you're doing. Like you're heading directly for the opposite bank. That's your idea. And if you don't look up at all, you just sort of go in that direction and you swim at 3 kilometers an hour. Then that's your velocity relative to the water, but it's not the actual velocity that you obtain. The actual velocity you obtain is the 5 kilometers an hour in the direction sort of across and down. Another way of thinking about that is to say, and this is probably a little bit hard to picture, but if there could be someone else, this sort of is like the train analogy, if there was someone else who was, I don't know, just floating along in a boat in the water beside you, then to them it would appear like you are swimming at 3 kilometers an hour directly across the river. Okay, because that would be their frame of reference, because they'd be traveling down the river at the same speed as you at that sort of 4 kilometers an hour. So to them, it could, if they couldn't sort of see the banks of the river, let's say, if it was a really wide river, if they were just watching you, it would actually look to them like you were going at 3 kilometers an hour in that direction across the river. Now, if we want to generalize that, so we could generalize that and we could say the velocity of an object, so this is the true velocity of A, which in our example is the true velocity of the swimmer. You can see that that's the vector sum of the velocity of A relative to B plus the velocity of B. I'll move that down a bit and actually write it in using our example. So in our example we had that the velocity of the swimmer, the true velocity, was equal to their velocity relative to the water plus the velocity of the water. So like I said, I've called that resultant velocity because really it's just the sum of the two velocities, but it's using that language of relative velocity. Now we can rearrange that slightly for the second situation, and this is where both objects are, we've got sort of two moving objects, let's just call it that. And this is where I'd use an example like two cars, let's say. So if you had, you were in a car, let's say, driving in that direction at 100 kilometers an hour, and there was another car driving this way at, so let's call that one car A and that one car B. Now if you were driving car A, or you were sitting in car A and you're looking back towards car B, it would appear to be traveling faster than 100 kilometers an hour away, or you'd appear to be going at more than 100 kilometers an hour away from each other. In fact, you'd be moving away from each other at 200 kilometers an hour, wouldn't you? So in this case we might say, what is the velocity of A relative to B? So the way I've worded that would mean we're sitting in car B, because it's relative to wherever we are. So we're sitting in car B and we're saying, what's the velocity of car A relative to us? Well, if we used the ideas here that the velocity of B is 100i and the velocity of A is negative 100i, because it's in the negative I direction, then we could say the velocity of A relative to B is actually equal to the velocity of A minus the velocity of B. So in this case, negative 100i minus negative 200i. So in other words, you're sitting in B, it appears to you that A is going in this direction at 200 kilometers an hour. And I think that one hopefully makes a bit of intuitive sense. And that idea relative to B, again, another way of thinking that would be to say it's the same as if object B was stationary and object A was traveling at 200 kilometers an hour in that direction. Now, I know this video is already a little bit long, but let me just give another example where they're not going in opposite directions. So what about if you were traveling, let's say, this direction here at, so call that one an example there. Let's go another example here. So what if you were traveling that way at 80 kilometers an hour and there was another car traveling this direction at 60 kilometers an hour. Okay, so 80 kilometers an hour and 60 kilometers an hour. And I've sort of put them tail to tail there, I guess maybe suggesting that they're both starting from the same place and they're heading in those directions. Okay, so if you were sitting in this car here, so let's call this car B and that's car A, and you wanted to say what is the velocity of car A relative to car B. So another way of saying that would be to say, if B was stationary, what would be the velocity of A, which would be the same as this scenario here. So if we use that idea that the velocity of A relative to B is equal to velocity of A minus the velocity of B, then using vectors we could say, okay, here's the velocity of A minus the velocity of B, so subtract B there, and that's going to give us this velocity of B of A relative to B. Okay, so that's what it would actually sort of appear to you if you're sitting in car B. It would appear that A is traveling at that speed in that direction. Okay, now again, using Pythagoras theorem like we did in that other example, we could say that's 100 kilometers an hour, because 60, 80, 100 is a Pythagorean triple. So it would be the same as you being still and car A traveling at 100 kilometers an hour in that direction. That would be the same thing that is going on in this scenario here. Alright, so we've got two different ways that the formula is expressed. This one here, and that's particularly useful when we're saying what's the real velocity of an object. So if you're sort of standing external and you're looking on to object, to the swimmer who's swimming across the river but being affected by the current, then it's good to have the formula in that method there. And then we've also got the formula in this form here, and that's particularly useful when we're actually saying, well, we're in a moving object and we want to know what the velocity of another object relative to us is. So our frame of reference is one of those moving things. Alright, that's a little bit of an introduction there to relative velocity.